Hello and welcome back everyone. In today's video, we will take a first look at the ideal boost converter transfer function in continuous conduction mode, the small signal model that forms the foundation of every compensator design. We will explore the three fundamental transfer functions: control to output transfer function, line to output transfer function, and output impedance. We will interpret their body diagrams using actual hardware parameters. Let's start with the three fundamental transfer functions of the boost converter in continuous conduction mode. Control to output transfer function, or GVD of S. This transfer function tells us how the output voltage responds to small changes in duty cycle. It is the core plant model used for compensator design, bandwidth selection, and stability analysis. Next is a line to output transfer function, or GVG of S. This describes how input voltage disturbances propagate to the output. It is critical for understanding a line regulation and for designing feed-forward techniques if needed. And at the end is also the output impedance, or Z out of S. This function shows how the output voltage reacts to changes in load current. It is directly tied to load transient performance and output capacitance selection. Although the numerators are different, all three transfer functions have exactly the same LC denominator. This is because they all originate from the same averaged state space model of the boost converter. The natural frequency omega 0, quality factor Q, and LC double pole appear in all of them. These transfer functions form the mathematical foundation for everything that follows: loop gain construction, type 3 compensator design, digital implementation on the C2000, stability and transient response analysis. On the next slide, we will look at the frequency response for the control to output transfer function, GVD of S. Now that we have seen the analytical form of the control to output transfer function, GVD of S, let's look at what it actually does in the frequency domain. Here is the same transfer function from the previous slide, but now expressed through its body diagram using the real hardware parameters of our converter. You can immediately see the three most important characteristics: low frequency gain GD0, a strong LC resonance peak determined by the quality factor Q, a minus 40 dB per decade roll off beyond the resonant frequency, phase drop approaching minus 180 degrees around resonance. But now we observe something fundamentally different compared to the buck converter. There is a right half plane zero at the frequency omega z. This zero increases the magnitude slope by plus 20 dB per decade, but at the same time it introduces an additional minus 90 degrees phase lag. This means after the right half plane zero, the slope changes from minus 40 dB per decade to minus 20 dB per decade, but the phase continues dropping further. However, because the phase continues decreasing, placing the loop crossover beyond the right half plane zero is fundamentally unstable. This non-minimum phase behavior is what makes boost converters significantly harder to control than buck converters. These are the parameters used for this plot. Inductance is 220 microhenries, capacitor is 20 microfarads, load resistance is 240 ohms, input voltage is 12 volt, and the output voltage is 24 volts. From these values, we compute GD0, Q, omega 0, and the right half plane 0 frequency omega z. These numbers match the markers on the plot, so DC gain at 33.62 decibels, resonance peak around 31.70 decibels, natural frequency around 7.5 kiloradians per second, and right half plane zero frequency around 273 kiloradians per second. Notice how the right half plane zero appears well above resonance, and observe how the phase drops further beyond that frequency. This transfer function, GVD of S, is the foundation of the entire compensator design. Every pole, every zero, and the final loop bandwidth of the Type 3 compensator will be chosen relatively to this plant. On the next slide, we will take a look at the frequency response of the line to output transfer function, GVG of S. Here is the line to output transfer function GVG of S along with its parameters and body diagram. Just like before, the denominator is the same second order LC system, but now the low frequency gain is simply 1 divided by 1 minus D. This means that input voltage disturbances are amplified by the boost conversion ratio. Here are the exact parameter values used for this plot, the same as in the previous slide. At low frequency, the gain is equal to 2, which corresponds to about 6.02 decibels. This tells us how much the input voltage ripple appears at the output in steady state. Next, we again see the LC resonance peak. Its magnitude is determined by the quality factor Q, which is roughly 31.70 decibels for this ideal converter. The resonant frequency remains the same. Above resonance, the slope drops at minus 40 dB per decade because this is still a second order system. This transfer function is important because it describes how input voltage disturbances propagate to the output. If your upstream supply introduces ripple, switching noise, or load interaction disturbances, this diagram tells you exactly how much of that noise will reach the output. Later, when we design the compensator, and especially if we use feed forward, this transfer function becomes key for improving line regulation performance. Before we finish, if you want to control your boost converter in voltage mode control and you don't want to start completely from scratch, you can check out my free boost converter toolkit on HK Academy. It contains LT-Spice models, Octave scripts, and C2000 examples that will help you get a working design very quickly. The link is in the description below. In the next video, we will continue this series and see how the series inductor resistance RL changes the transfer function and how it modifies the body diagram of the boost converter. Thanks for watching, and I will see you in the next video.